The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next presenter is going to be Dr. Byard, and he will speak to us on early age autogenous effects in internally cured concrete and mortar. Dr. Byard is a staff at the faculty member at the University of Tennessee in Chattanooga. He received his bachelor's and master's from Tennessee Technological University, and he got his PhD in civil engineering from Auburn University in 2011. He is an associate member of Committee 231 that co-sponsored this, and also of Committee 213 that is also co-sponsored. Without further ado, please help me welcome Ben.
Thank you very much, George. Like you said, my name is Ben. The paper that I'm presenting today is Early Age Autogenous Effects in Internally Cured Concretes and Mortars. My co-authors were Dr. Schindler and Dr. Barnes at Auburn University, and like you said now, and so all this work was done at Auburn, was part of my PhD, and now I'm at the University of Tennessee, Chattanooga. All right, so the presentation objectives today, we're going to cover just a snippet of what was actually presented in the paper because, like Eric, there's just not enough time to go over the whole paper. So we wanted to, today for this presentation, we're going to evaluate the effect of internal curing and water-cement ratio on the development of stress and internal relative humidity. And also we're going to evaluate the effect of internal curing and water-cement ratio on autogenous shrinkage development in concrete and mortar, to see what the difference is between the two. All right, so the outline, pretty straightforward. We're going to talk about stress development mechanisms, the testing equipment that we had at Auburn, the experimental work we did, results, and conclusions. All right, so this is kind of simplistic here, but why does concrete crack? Well, when you place concrete in a restrained condition, such as a bridge deck or a slab on grade, you get restraint from either the base, in the case of a slab, or a girder in the case of a bridge deck. So when you have that restraint and then you have these volume changes that occur naturally, you get stress development. When that tensile stress exceeds the tensile capacity, then you have cracking occur. So why do we have early age volume changes? Well, it can happen for a couple of reasons. One is thermal effects, which is, something changes temperature, it wants to expand. When it heats up, it wants to shrink when it cools down. And so at early ages, that's primarily going to be heat of hydration. And that's going to be a function of the coefficient of thermal expansion, so different concrete proportions are going to have different CTEs. In addition, you can also have a decrease of internal relative humidity. And one of these we're real familiar with, drying shrinkage, which is moisture leaving the concrete, going into the atmosphere. And so we're all familiar with that. But then you can also get decreased internal relative humidity due to self-desiccation, which is the consumption of water by the continuing cement hydration. And that's going to lead to autogenous shrinkage, or one of the reasons why we get autogenous shrinkage. So a closer examination of self-desiccation here. Here's a simplified cement water model here. You have your cement, perfectly spherical cement grains, which isn't possible, but it makes a pretty picture. So we have our cement and water. And this is T equals 0, cement meets water. And we jump forward in time to initial set. So at initial set, we have hydration products that are bumped into one another now. You're starting to get a rigid skeleton forming. And since we have chemical shrinkage, which is about 7%, the hydration products are smaller than the initial grain of cement. And so because of that, you're going to have a decrease in volume due to this chemical shrinkage. This is imperceptible before set because there's no stress, so these are just kind of cement particles floating around in a solution. So there's no stress generation because there's no rigid skeleton yet. So what you get is just an imperceptible, almost settling of the slab or what have you, and it's, nobody really cares about this shrinkage. But what we do kind of start to care about here is later in the cement hydration here, a good time after set, we have a lot of hydration products now bumping into one another. And we continue to have this chemical shrinkage. But since we have this rigid skeleton, we can't just settle a little bit. And so what we get is we get the formation of capillary pores. And so this chemical shrinkage causes these vapor-filled pores. And as the cement continues to hydrate, it starts consuming this water out of these pores. And so you get a similar effect that you do with drying shrinkage, which is these capillary pores dry out, but with just simply with drying shrinkage, it's going into the atmosphere. Now it's being consumed by the cement. So this happens in a completely sealed system. So we're going to have an additional decrease in volume due to the capillary stress. So these pores are drying out, we get capillary stresses, and we get this additional shrinkage just due to capillary wall stresses. Now, with the introduction of some internal curing media, in this case I have a pre-wetted lightweight aggregate, what you get is you get moisture movement from the lightweight aggregate into the hydrating cement paste. And so what it does is it prevents or reduces these capillary stresses by keeping those capillaries full of water or vapor. And so because of that, we get the shrinkage there is going to be reduced by limiting these capillary stresses. And so what we found that water can move about 0.12 inches. And in addition to this reduction in capillary stress, we're also keeping these cement grains moist. And by doing so, we're increasing their degree of hydration, because when you get these pockets of desiccation around the cement grain, it doesn't hydrate as well. And so by keeping a good high internal relative humidity, then you're going to get a higher degree of hydration. All right, so what I just said there is why use lightweight aggregate? Well, when you batch it in the pre-wetted state, lightweight aggregate has all this internal water. And so this internal water promotes additional hydration, more internal curing. And these saturated or pre-wetted lightweight aggregates may alleviate some of these capillary stresses. So you're going to reduce this autogenous shrinkage by keeping those capillaries full of water. All right, so let's look at the testing equipment here. All right, so we measured the stress development, and we did this with our rigid cracking frame. So essentially you have this large concrete dog bone. Its cross-section is 6 by 6. If you stand that puppy up, it stands about as tall as me, so about 6 foot tall with dog bone with gauge length and everything. So we cast it in this formwork, sealed formwork, and inside that formwork we have these copper cooling pipes. Boom. You can see it there. You have some copper cooling pipes. And so because of that, that allows us to control the temperature of the sample. So we can run it through whatever temperature regime we would like. And as it undergoes these volume changes, it's restrained by those large 4-inch diameter steel bars. And so here they are in real life. You can see the hoses there that circulate our temperature control fluid, which is water and ethylene glycol. And so you can see somebody finishing it there. And like I said before, it's perfectly sealed, so there's no moisture movement in this system. And then we can control its temperature with those large temperature control baths. And so that's how we measure the stress development in these rigid cracking frames. And to measure the free shrinkage in concrete, we had these free shrinkage frames, which were developed by Byard. We kind of borrowed his design and built it there at Auburn. But what we have here is we have a 6 by 6 cross-section box. We place 2 layers of plastic. We put oil in between the plastic. We place the concrete in there. And then we have some LVDTs that we attach, embed into the sample. And then we cover it and we seal it. So once again, there's no moisture movement to the atmosphere. It's also temperature controlled, so we can run it to the same temperature regime as the rigid cracking frame for the stress development. So we can get the stress development and the unrestrained movement of the sample. And for the free free strain of the mortar, we measure that with the corrugated tube method, ASTM 1698. So that's how we captured the free strain of the mortar. All right, so let's look at the experimental work that we performed there. So each mixture was tested for the restrained stress development. And we did this at an isothermal condition. So we used those cooling pipes of the early ages to keep the temperature down and hold the temperature constant at 73 degrees F. And so what that means is we have no stress development due to thermal stress. We have no stress development due to drying shrinkage. The only stress development that we're capturing with this setup is autogenous stress development. So this is that water being consumed by the cement hydrate. And so we used our rigid cracking frame to do that. For free shrinkage, we also did that at isothermal. And so for the concrete, we used our free shrinkage frame. And we held that at an isothermal condition also. And for the mortar, we used the corrugated tube method. And one thing I want to point out here is we use sieved mortar. So for the restrained stress development, the free shrinkage, this was all one big batch of concrete. And so for the mortar, we simply sieved it on a number 4 sieve, which deviates from the specification. You're supposed to mix a special mortar batch to fill the corrugated tubes. We just sieved it. And we measured internal relative humidity. We did this with embedded relative humidity sensors. Those were also held at isothermal condition. We measured the mechanical properties, but I'm not going to present any of that data because there's simply not enough time in the 20-minute presentation. All right, so the mixtures we tested, we had 3 water to cement ratios, 0.42, 0.36, and 0.30. All these, the slumps were between 3 and 5 inches, 4.5 to 6.5% air. We used silicious river gravel and natural sand in all of these mixtures. And so for each control mixture, we had a series of internal curing mixtures. And so they had the same slump, the same air content, the same normal weight aggregates as the control, but we simply replaced a fraction of the normal weight sand with lightweight sand. And so we had a couple of requirements that we wanted to meet, and first, or one of them I should say, was the 135 pounds per cubic foot. And so that's normal weight concrete as per the AASHTO LRFD bridge deck. So we wanted all this to be normal weight concrete. We didn't want specified density. So all these mixtures are normal weight. And also, we wanted to use the Vince method for lightweight aggregate proportioning. And all that is simply calculating the chemical shrinkage volume and then supplying an equal volume of internal curing water. And so for our 0.42 mixtures, just because of their proportions, if we used the Vince method on all of those, we would be less than 135 pounds per cubic foot. So for the 0.42 mixture, as you see here, we simply used the maximum replacement of fine aggregate with lightweight aggregate that would give us a calculated equilibrium density of 135 pounds per cubic foot. And so that did something interesting. The 3 lightweight aggregate sources that we used, shale, clay, and slate there, they each had different absorption capacities, specific gravities, and so they all weigh 135 pounds per cubic foot calculated equilibrium density. Due to their different absorption capacities, they provided 3 levels of internal curing. Shale, clay, and slate. The shale provided the most, the slate provided the lower level of internal curing. And so you can see our internal curing water provided there from each of them, and that's pounds per cubic yard. Something else I want to point out here, with all these mixtures, the paste volume was the same, the coarse aggregate volume was the same, and the total fine aggregate volume was the same. So fractionally, all these mixtures are the same. We just switched out a little normal weight with a little light weight. Here's our 3.6 and 3.0 mixtures. We had 2 levels of internal curing, a high and a moderate. And so you can see the internal curing levels here. So the ICM and ICH actually stands for internal curing by the Mills and Hansen method. So if you read the paper, those are 2 different methods to calculate the chemical shrinkage, essentially. But it also works out that one provided a moderate amount and one provided a high amount, and so we'll just go with that for now. And once again, all these mixtures, the 0.42, 0.36, 0.30, have the same coarse aggregate volume, the same paste volume, and the same fine aggregate volume. And so when we got to a lower water to cement ratio, essentially all we did was keep the same paste volume and change the proportion of cement and water. So from a stress development point of view, their volume fractions are identical. All right, so let's start looking at some results here. Here's the autogenous strain of concrete and mortar. So you can see the black lines are concrete, the gray lines with the colorful dots are mortar. And so for the concrete, that was measured with our pre-shrinkage frame, and for the mortar, that was measured with the autogenous tubes, the corrugated tubes. And so what you see here is that the order is the same. The 0.42 strained the least, followed by the 3.6, and the 3.0 had the greatest amount of strain. And so what we have here is, as you get a decreased water-cement ratio, you start getting smaller capillary pores. And you get a lower density. That's one of the reasons we like low water-cement ratio mixtures, is because they have low density. Or low permeability, pardon me. So you have smaller capillary pores, you get lower permeability. But what you also do is smaller capillary pores, when they dry out and they desiccate, they create greater capillary stresses. So those small pores are great for permeability, but when they dry out, they produce more stresses from a capillary stress point of view. So as we get to these lower water to cement ratios, they have increased free strain because they have those smaller pores, and when they dry out, they produce more stress. And you can see that the concrete strains less, and the mortar strains a little more. So what happened there is all this autogenous shrinkage stuff is a paste thing. It's happening in the cement and water, and it's being restrained by the aggregate. The aggregate can care less what's going on in the paste. It wants to stay its volume. The paste is undergoing this volume change, and it's being restrained by the aggregate, essentially. And so the concrete has coarse aggregate, which provides more restraint than fine aggregate. And so your concrete is essentially it's restraining the movement that's occurring in the paste. The mortar didn't do as good a job, and so it has a greater strength. All right, and so here's all mortar specimens here. This is the 0.42. So the black line there, it strained the most, and then these different levels of internal curing mitigated different amounts of that strain. And one thing I want to point out, the clay and the slate have a similar level of mitigation, but the clay lightweight aggregate that we use was actually an intermediate. So it had some 3/8 inch particles. So when we sieved it to get the mortar sample, we're actually pulling out internal curing water by removing those bigger particles. And so even though the clay had more internal curing water, it mitigated the stress about the same as the slate. And that was kind of just the nature of the test that we did when we said that we pulled out some of those 3/8 inch particles. All right, here's the 3.6. The 3.6, it had more autogenous strain than the 4.2. And then you had your ICM, which was our moderate level of internal curing. Mitigated most of it, but not all of it. And then the ICH, which was our high level of internal curing, mitigated all of this autogenous strain. All right, 3.0, this was our lowest water to cement ratio. You see really similar trend here. The moderate level of internal curing mitigated most of it. The high level of internal curing mitigated all of the strain. All right, so now we're getting into the stress development. So far we've been looking at the driving force, essentially, the volume change. And so now we're looking at the stress development. So this is our rigid cracking frame. And what we have here is our 0.42 water-cement ratio in 4 days held isothermally, so there's no temperature change involved here. Developed 50 psi of stress development. I should also point out that 0.42 is generally in literature, they say this is the point when you have to start kind of thinking about autogenous shrinkage and autogenous stress development. So this is sort of the bottom level of when you start worrying about this a little bit. And so we had 3 levels of internal curing, and it just, the ranking falls right in line with the internal curing water provided. The shale, which provided the most, is actually in compression. So it's completely precluded from developing these tensile stresses because of the internal curing water provided. And then our clay and our shale. Then our 0.36, at 4 days, it developed 150 psi, which is kind of starting to be a problem, of no temperature change, completely autogenous stress development. And then our ICM mitigated most of it, and our ICH, our high level of internal curing, mitigated almost all of that autogenous stress development. And so here we have 0.30, 250 psi in 4 days, completely isothermal, which is kind of a big problem. And then our ICM and ICH mitigated, equally well there, the stress development. So they're about 25 psi. All right, so when we compare the amount of internal curing water that we provide with the isothermal stress development compared to the control, as you increase your internal curing water, you get more reduction, which kind of makes sense. But you can see with the 3.6 and the 3.0, you reach a plateau. The 0.42 might blow your mind a little bit with 130% reduction, but all that is that shale mixture that went into compression. It mitigated 100% of the tension and then another little 30% by just virtue of going into compression there, so that might be befuddling. But if we added more, then it would also plateau. You start getting diminishing returns after you get this stress developed, or this stress reduced, then you start you reach that plateau like you see in the 3.6 and 3.0. All right, so here's a really cool slide. I like this a lot. This is the scaled internal relative humidity, so we scaled it at 18 hours. And you see this is the reduction in internal relative humidity. So this is the whole driving force. Our pores are drying out, our relative humidity is being reduced, we're getting capillary stresses, we're getting this autogenous volume change, and then if it's restrained, we get this stress development. So you can see the ranking of the 0.42, 0.36, and 0.30 increasing stress development, and then you can see the exact same ranking in very similar orders of magnitude between them of the decrease in internal relative humidity. So there's the driving force, there's the effect. It dries out, you get stress. All right, so let's look at the conclusions here. Mortar has a greater autogenous strain than that of concrete due to the restraint provided by the porous aggregate. As the water-cement ratio decreases, autogenous stress and strain increase, and that's due to the smaller pores. The use of pre-wetted lightweight aggregate reduces or eliminates the stress development and strain caused by autogenous shrinkage. Thank you for your time.
We do have a time